Hi friends, I am Prabal Chakraborty. Today my discussions is very large. My discussions is based on linear algebra. It is matrix algebra and diagonalizations. So friends, before this that I in my linear algebra first theoretical chapter I described eigenvalue, eigenvectors, everything. Now I will discuss that properties of rank. Properties of rank. Properties of rank. The rank of every non-singular, the rank of every non-singular matrix, singular matrix of order n is n. Number one means if a det a value does not equals to 0 and a is n cross n matrix, then rank of a is equal to n. Always remember this, friend. This is the very important, because this every properties is very important. Why? Because when you will go to solve competitive examinations, this type of questions, this property is coming a lot of questions. That's why I want to discuss this because you have to remember this. If you will forget, then you cannot give an answer properly in your exam. Okay, the rank of a square matrix A of order n can be less than n, even only if a is singular. That is, a mod of a is equal to 0. A is singular means a is n cross n matrix, friends, and det of a is equal to 0. Then rank of a obviously less than n, because there is only one 0 their eigenvalue is one eigenvalue, at least one eigenvalue is 0. That's why rank of a less than n. Number 3, the rank R of n m cross n matrix can at most be equal to smaller of the number m and n, but it may be less. Because friends, must remember, R is if rank of R is matrix m cross n, must remember that R value less than or equals to mean of m comma n. Means this is that they ask. It may be less or may be equal. Mean value means smaller value of the m and n. Okay. Number 4, the rank of 0 the rank of zero matrix is taken as 0. The rank of zero matrix is taken as 0. Number 5. If I is a matrix, of order n, then it is equals to n. I means unit matrix. I is a unit matrix of order n, then its rank is equal to n. Number 6. Elementary transformation do not alter the rank of matrix. Elementary transformation. Elementary transformation do not alter the rank of matrix. Number 7. If A is a square matrix, of order m, then m rank A is called the nullity of the matrix. Nullity of the matrix means it is denoted by NA. NA is denoted by NA. Okay, next. A is number 8. Rank of A, rank of a matrix is same as the number of linearly independent linearly independent row vector in the matrix. Row vector in the matrix as well as the number of linearly independent column vectors. Row vector and column vectors in the matrix. Okay, this is very simple. You have to understand the concept. A is equal to, I can write 1 2 3 4 5 6 0, 0, 0. Friends, this is very, very simple, that linearly independent. Linearly independent means you have to choose. Linearly independent means C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 is equal to 0. Then C1 is equal to 0 and C2 is equal to 0 and C3 is equals to 0. Then if here you see that linearly independent, okay, it is very, very simple. I can write it is not 0, 3, 4, 6 I write. Okay, here 3, 4, 6 and 3, 4, 6 are linearly dependent. Okay, linearly dependent. 3, 4, 6, 3, 4, 6 are same, means they are, but this vector and this vector, this is the row vector. Row vectors means row alpha 1 is equal to, let's say, 1, 2, 5. This is a row vector, and alpha 1 and alpha 2 is equal to 3, 4, 4, 6. This is the row vector. Now you can get a relationship such that C1 alpha 1 plus C2 alpha 2 is equal to 0. Then you can easily show that C1 and C2 is equal to 0. Then means row of rank of A is equal to 2. Another example, and this is the column vector, and if you will see the column vector, you can get that same way. There is also two linearly independent column vectors also. Means same here, row vectors and independent row vectors and independent column vectors. Independent row vectors, linearly independent. This is the linearly, I write linearly independent and row vector, and linearly independent column vector. This is the simple, and if you will see that linearly independent means this way. So I hope it is clear for everyone, and I will go next. Number 9, the rank of a matrix A does not change by pre-multiplications. Pre-multiplication or post-multiplication with any non-singular matrix. Post-multiplication with any non-singular matrix. Non-singular matrix. Example, A is equal to, same example, 1, 2, 3, 4, 5, 6, and it is also 1, 2, 3. Here rank of A is equal to 2. Rank of A is equal to 2. Then you can see that rank of A is equal to 2, and A is, and if you multiply K is any square, then rank of Ka is equal to also 2. Means K means you can multiply 3, 4, 5 and post multiplications, everything, pre-multiplication or post multiplications with any non-singular matrix, but rank will not be changed. Number X. If A and B are matrices of some order of some order, then rank of A same order, okay, same order, their order is same, then rank of A plus rank of B less than equals to rank of A plus rank of B. Number 11. If A and B are matrices of same order, then rank of AB, rank of A comma B, rank of AB less than equals to mean of rank of A and rank of B, where rank of AB, AB less than equals to rank of A and rank of B less than equals to rank of AB less than equals to rank of B. Number 12. If A dash is a transpose of matrix A, then rank of A dash is equal to rank of A, and that implies rank of A dash is equal to rank of A, both are same, rank of A. And if A theta is a matrix of order m cross n, then rank of A less than equals to mean of rank of m comma rank of n, means thus rank of A less than equals to m and rank of A less than equals to n, that I described. I also described A theta is a matrix. And another fact that x triple I that rank of AB less than equals to rank of A plus rank of B minus n. This is the one of the property. Now I shall go to the algebraic multiplicity. I am discussing algebraic multiplicity. Multiplicity. Algebraic multiplicity. Algebraic multiplicity means algebraic multiplicity means, suppose the characteristic equation A can be written as lambda x minus lambda I R1 lambda 1 R1 x minus lambda 2 R2 dot x minus lambda n Rn. Then friends, algebraic multiplicity of the lambda 1 of lambda 1 is R1. Algebraic multiplicity of lambda 1 is equal to R1. And geometric multiplicity, now I am coming geometric multiplicity. Geometric multiplicity means geometric multiplicity means geometric multiplicity multiplicity of lambda 1 is equal to number of linearly independent number of the linearly independent vector, number of linearly independent eigenvector. This is the eigenvector. Number of linearly and independent eigenvector means n minus rho into a minus lambda 1 I. This is the n minus rho into a minus lambda I means card, I can write card rho into a minus lambda I. This is the kernel property is nullity. So GM is equal to geometric multiplicity of lambda 1 and number of linearly independent eigenvectors, and number of linearly independent eigenvector means n minus rho into a minus lambda 1 I means kernel rho into a minus lambda 1. This is the very, very important, because a lot of questions is coming from the algebraic multiplicity and geometric multiplicity, friends. And let's discuss let's give one example. This is the 1 2 3 0 0 0, and number it may be any number. I can write I can write 2000 to 20 30 50. Now you can see that algebraic multiplicity m, okay, this is the 1. Algebraic multiplicity of 1 is equal to 2. Same fact, because eigenvalue is 1 2 1, and algebraic multiplicity is number of the eigenvalue. Number of eigenvalue is 2. So algebraic multiplicity of 1 is equal to 2. But when I go to the geometric multiplicity, geometric multiplicity, so you how can you will get multiplicity? This is the very, very simple multiplicity. How can I find out? This way, that whatever I say n minus rho into a minus lambda 1 I, so means number of linearly independent eigenvector of lambda 1. Eigenvector lambda 1. So how can you can get n in here. N is 3 cross 3 matrix, so it is 3, and when you will multiplication row and subtract it 0 0 0 2 0 0 and 20 30 and 50s, then the value you have to get when I will measure the rank, you will see that this determinant value is 0, not 0. To 50 into 20, this is the 50 into 20 means 100, and another is 2 into 30. So this rank is 2. So 3 minus 2 is equal to 1. That's why GM is equal to GM of 1 is equal to 1. GM of 1 is equal to 1. So this matrix is not diagonalizable. diagonalizable. I will discuss that when is the diagonalizable condition is one, that m is equal to, when m is equal to gm, then the matrix is not diagonalizable. Okay, thank you. Now I will tell about the idempotent matrix. Idempotent matrix. Idempotent matrix is the property A square is equal to A, and that implies A is idempotent matrix. A does not equals to 0 or may be 0. A equals to 0 or A may be 0. 0 matrix is also idempotent matrix. Okay, because it is follow also this, and also another factor is fx is equal to characteristic equation is equal to x square minus x, means characteristic equation A, and minimal polynomial. This is number 1. Number 2, I just discussed property of idempotent matrix. Property. Number 3 is minimal polynomial. Okay, what is minimal polynomial? Minimal polynomial means smallest monic polynomial. Okay, monic means, suppose x square plus x plus 2, this is minimal polynomial. This can be minimal polynomial, but it is not a 5x square plus x plus 3. This is not minimal polynomial. It is not minimal polynomial. Monic polynomial means highest degree of the polynomial is coefficient of the highest degree of the polynomial is unit. Unit means 1. This is not minimal polynomial. So it is minimal polynomial. It can be minimal polynomial equals to 0. It can be minimal polynomial, but it is not minimal polynomial, friends. Minimal polynomial become mx is equal to x and equals to x minus 1 and equals to x square minus x, and this is it can be minimal polynomial. And if a does not equals to 0 and a does not equals to I, then minimal polynomial obviously x square minus x. Minimal polynomial must be x square minus x. And number 4 is I minus a whole square is equal to I minus a if a square is equal to e. Number 5, this is the property. Okay, row a plus row I minus a equals to n. And number 6, a square is equal to a and date a does not equals to 0, then e is equal to I. So it is that we conclude that only identity matrix is non-singular matrix. Non-singular matrix of idempotent matrix. Must remember, idempotent matrix, if it is say the non-singular, then it is obviously identity matrix. Okay, and every idempotent matrix is singular except identity matrix. Identity matrix is only one where it is non-singular matrix, means det A does not equals to 0. That I prove in here. This is say, and this type of questions is coming in CSIR, NET, GATE, a lot of examinations. Those who are preparing, they know, and I am also preparing for my study. Then they know that identity matrix is non-singular, and others every matrix is singular matrix. Singular matrix means det A equals to 0. Definition of the, now I will go definition of similar matrix, because I am going to the diagonalizations, because my discussions is diagonalizations. Okay, so before the diagonalizations you have to know similar matrix. Similar matrix, suppose A and B are two square matrix. Matrix of size n. Then A and B are similar. When there exist S who such that det S does not equals to 0, then A equals to S inverse A is equal to S inverse BS. Then we can say A similar to B. Similar matrix is very, very important concept of the linear algebra. Linear algebra, a lot of questions is coming from linear algebra in CSIR net examinations. And another fact that in the similarity holds reflections equivalent relationship. Okay, equivalent relation. Similarity holds equivalent relations, means A is similar to B, that means B similar to A. It is called symmetric. Equivalent means reflexive, symmetric and transitive. This property will hold, number 1. Number 2, A similar to A, that implies its hold reflexive property. And number 3, A similar to B, that and B similar to C, that means, that implies A similar to C. This is called transitivity property. So friends, it is clear that similarity hold when it is equivalent relationships. And let us discuss diagonalizations. Diagonalizations of matrix. Diagonalization of matrix. Very simple, friends. When you will get diagonalization means diagonal form. Diagonal form is D. Suppose D can be written as A1, 1, A2, 2, A3, 3, and all are 0. All entries are 0, but only diagonal entries are non-zero. then it is called diagonal matrix. I discuss also in my class what is diagonal matrix. What is diagonal matrix? So it is clear for everyone. Then now I get a P is a matrix and date P does not equals to 0, then A is called diagonal matrix when D is equal to P inverse AP. Okay, when D is equal to P inverse AP, then this is called diagonalized matrix. Okay, and here P is non-singular. Next I go one questions which is coming from CSIR NET 2014. Okay, before this I will discuss Jordan block and Jordan canonical after solving this problem. Let's see. I think that it is clear for everyone. My questions is clear for everyone. I think I hope that everyone see my questions and pause it and write these questions clearly. Okay friends, I hope you will write, and now I will discuss. Let A be a 4 cross 4 matrix over C such that rank of A equals to 2. I mark. This is the 4 cross 4 matrix, friends. This is very important information. And rank of A is equal to 2. This is very important information. And after that it is called A cube is equal to A square does not equals to 0. Suppose that A is not diagonalizable. It is also very important information. A is not diagonalizable. One of the Jordan block of Jordan canonical from A is 0, 0, 1. This is also one question. Another question is to number 2, A square is equal to A. A square is equal to A does not equals to 0. Number 3, there exists a vector such that AB does not equals to 0 but A square V equals to 0. The character polynomial of A is x to the power 4 minus x cube. So friends, this is very conceptual questions. You have to know a lot of things, a lot of knowledge to solve these questions. At first it is discussed then idempotent matrix. At first you see A square is equal to A. I also discussed in my class idempotent matrix. Okay, I discuss idempotent matrix. Idempotent matrix is A square is equal to A square is equal to A. In here you will see that A square is equal to A does not equals to 0. A square is equal to A does not equal to 0. There exists a vector such that AB is equal to. So friends, must remember that 4 cross 4 matrix not diagonalizable, and Jordan block, Jordan canonical form is Jordan block and Jordan canonical form. This is, and A square is equal to A. So I tell number 1, A square is equal to A means idempotent matrix. Idempotent matrix, and idempotent matrix is always diagonalizable. Is always diagonalizable. And number 2, that so this cannot be hold. This cannot be hold. This number 2 is not right. This is the CSIR NET. CSIR NET questions is always very conceptual questions they ask, and you have to know the theory as well as you have to follow the all concept, then you can solve this problem. Number 2, one of the Jordan block is Jordan canonical block. Okay, now let's see that A cube is equal to whatever they say, a cube is equal to a square, a cube is equal to a square. Okay, so I get x cube minus x square, characteristic equation. Characteristic means CHX, characteristic equation. Equation is x cube minus x square, and minimal polynomial. Minimal polynomial mx. Possible minimal polynomial number 1 x square, x minus 1, and another is x into x minus 1. This is the possible minimal polynomial. And another is x square into x minus 1. Let's see. Whatever x minus 1 and x minus 1 and x into x minus 1, both are linear factor. Linear factor. And we know that linear factor, if the eigenvalues, if minimal polynomial is a linear factor, then it is, if the minimal polynomial are linear factor, it is diagonalizable. It is diagonalizable. So friends, my possibility x square is equal to 0, minimal polynomial x square is equal to 0, and x square minus x square into x minus 1 equals to 0. This is my total possibilities. Total possibilities this minimal polynomial. Total possibilities is this. So friends, if we see that whatever I have to do the Jordan canonical block, minimal polynomial. My possibility x square is equal to 0 is also not diagonalizable, and another fact, x square into x minus 1 equals to 0, it is also diagonalizable. And here rank of A is equal to 2, so x square equals to 0 is cancelled. Rank of A is equal to 2, so x square is equal to 0, it is not possible. So row A is equal to 2. So my minimal polynomial should be x square into x minus 1. X square into x minus 1. And characteristic equation should be CHX, sorry, it is not characteristic equation, x cube minus I can write this the polynomial way, and characteristic equation CHX is equal to x cube x square into x minus 1 whole square. X square is equal into x minus 1 whole square. This is the polynomial, as it is 4 cross 4 matrix. As it is 4 cross 4 matrix. Therefore, I will write this. There exists one block of order 2. One block of order 2, which is one block of order 2 means in here x square into x minus 1 and our characteristic equation is x square, the Jordan block one block is order 2 means 0 in case of 0. So my one equation, one of the 0 eigenvalues, this order, this is the possibility. So the first order is correct, means 0 0 0, because the rule of the, I will discuss the rule of the Jordan block, that at least one, there exists one block of order one block of order 2 order 2 whose eigenvector eigenvalue is 0. So this is possible. Now again we are discussing that in case of minimal polynomial, we get whatever we get, minimal polynomial is x square into x minus 1. This is our minimal polynomial. It is possibility. Another is not possible, and we get that according to the minimal polynomial 0 0 0 1 is possible. So possible Jordan block is, I write, one is if the characteristic equation x square into x minus 1 whole square, then it should be 1 1 0 1, and another part is 0. My Jordan block will be this. This is my Jordan block. 1 2 1 2 1 1 1 1 means my Jordan block is x square into x minus 1. My Jordan block is this is my possible Jordan block. 1 1, my Jordan block will be 1 1 and 0 0 1 0. This is my possible Jordan block when the characteristic equation CH characteristics of x is equal to, when my x square into x minus 1 whole square. Okay friends, this is my possible Jordan block. Another is characteristic is another possibility is characteristic x is equal to x cube into x minus 1, x cube into x minus 1. Then my Jordan block, possible Jordan block will be 0 1 0 0. This is the Jordan block. One another is, as the minimal polynomial is 2, so my possible one should be this, another should be 0, and another should be 1. This is my possible Jordan blocks. As the rank of A is equal to 2, let's see friends, rank of A is equal to 2. Okay, and in here rank of the Jordan block is 3, and in here rank of Jordan block is 2. So this is not possible. My characteristics equation should be, this is the possible. So friends, my answer should be, this is my answer. Number 4 is correct, because x to the power 4 minus x cube is, if this relationship it will be characteristic polynomial, then friends a cube is, then rank of A is equal to 2, and a cube minus a squared, this is also be true. So my possibility characteristics polynomial of A, so x to the power 4 minus x cube is correct friends. Yeah, and now I have to see number 3 is correct or wrong. Number 3, I will go number 3. A is equal to, what will be A? A is my 0 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1. This is the Jordan block. This is my Jordan block A. This is my matrix A, and another is A B C D. I choose A B C D. V means V is A B C, and also you can say D. So it is A B C D. If I will multiply, then whatever I get B, and another I get whatever I get, another is I get 0 0 0 D. 0 0 0 D. So the friends, here B does not equals to 0. I get AV does not equals to, this condition hold in here, this condition hold, and now I have to see A square V. What is the A square? A square, if I will multiply A into A, then whatever I get 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1. This is my A square, and V is my then you can get whatever I get. If I will multiply 0 0 0 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0 1, and multiply with A B C D, then equals to, then we can get 0 if D equals to 0. D equals to 0. So friends, they ask that there exists a vector such that AV does not equals to 0, but A square V is equal to 0. So it is possible. So my answer is 1, 3, 4, and 2 is not possible because it is A square is equal to A. A square is equal to A is diagonalizable, idempotent matrix. I discussing. Now I am writing diagonalizable, means Jordan block. Jordan canonical form property. Okay, this is the very important property. Number of Jordan block is equal to upper triangle. Number of Jordan block is equal to upper triangle. Yeah, and Jordan block can be written this way: A11 A0 A22, this way. Jordan block can be used, and another is everything is 0, and this way Jordan block can be written. Jordan block is one kind of normal form. I will discuss A2n up to this and this way you can write. Jordan block can be like this is the one upper triangle, and number 3, T such that V tends to V. Be a linear operator. Where del T is equal to T minus lambda 1 whole to the power 1, T minus lambda 2 whole to the power n2, and T minus lambda r whole to the power nr, and MT means minimal polynomial is equal to T minus lambda 1 whole to the power m1, T minus lambda 2 whole to the power m2, T minus lambda r whole to the power mr, where n1, n2 up to nr is equal to algebraic multiplicity, algebraic multiplicity, and there exists, and gm I also discussed, gm is equal to linearly, number of linearly independent vector, eigenvector, number of linearly independent eigenvector. Number one, there exists one block of order mi and order and of the other jb less than equals to mi. Friends, must remember that mi means power of the minimal polynomial. You see that here this sum you see that x cube minimal polynomial is x square. So one of the Jordan block should be 2. That's why 0 1 0, this is the Jordan block, 2 plus 2 matrix, order 2 cross 2 matrix. Order of the one of the Jordan block order should be 2 cross 2 matrix. That's why this first option is correct, 0 1 0 0, because minimal polynomial of the polynomial x square means x minus 0 whole square. Eigenvalue 0, power of the eigenvalues 0 is 2, so that here you see 0 0 0 1 0 is the minimal block, 2 plus 2 plus 2. So I take this. Another number second is the sum of orders b, the sum of order of jb is equal to ni. The sum of order jb is equal to ni. The number of jb is equals to the number of jb will Jordan block, the number of the Jordan block will be equal to gm, equal to the gm of lambda I. So friends, this is the main fact, that number of the Jordan block of the gm means in here, in this case, whatever I get, in case I get our Jordan block is, this is our Jordan block. Okay, so number of gm of 0, in here gm of 0 is equal to 2 and gm of 1 is equal to 1. Okay, and gm of 0 is equal to 2, but am of 0 is equal to 3. That's why it is not diagonalizable. In case of diagonalizable, am equals to gm, because you see this a characteristic equation of this polynomial is x cube x to the power 4 minus x cube is the characteristic equation. Characteristic equation means in here x cube and x minus 1. X cube means 3 is the Jordan gm of 1. So it is the main fact, you have to remember. And suppose del t, I will give another example. Del t is equal to t minus 2 whole to the power 5 and t minus 5 whole to the power 4 means characteristic equation. And minimal polynomial is equal to t minus 2 whole cube and t minus 5 whole to the power cube. Then we get 2 1 0 2 1 0 0 2 1 0 0 2. This is 1 3 cross 3. It should be must, because our highest degree according to the question, one block of a block should be my and others should be less than mi. So one block should be this 3 cross 3 and other should be 2 0 1 2. If gm is equal to gm of 2 is equal to 2, and another should be 2 1 2 0 2 0 0 2 0 1 and 2 2, then this is gm of 2 is equal to 3. So friends, thank you for watching. Goodbye.